Hi, I'm Destry Monk, and I'm going to be talking about the Zeeman Effect. What is the Zeeman Effect, you might ask? It is the shifting, splitting, or partitioning of atomic or orbital energy levels caused by an external applied magnetic field. Why is this important? It's because it gives us a better understanding of the intricate architecture of atoms and other particles, as well as it gives us as students more insight into the workings of the Stern-Gerlach analyzers that we saw in Chapter 1 of McIntyre's quantum mechanics book. Those analyzers operated entirely off of the spin magnetic number, whereas here we're going to focus first on the normal Zeeman effect, which neglects spin and focuses entirely on orbital angular momentum. And then we'll look at the anomalous Zeeman effect, which is really just the full Zeeman effect. And that accounts for both orbital angular momentum and spin angular momentum. What happens when a particle passes through a magnetic field is that the magnetic field couples to that particle's magnetic moment, which has as a factor the magnetic quantum number, m. Here is going to be m sub l. And so for a hydrogen atom in its p state, it has an orbital magnetic quantum number, an orbital momentum quantum number, L, equals 1. And so m sub L can range from L to negative L by integer values. And so m sub L can equal 1, 0, and negative 1. And so where we previously have just a single energy, now we have 3, 1 for m sub L equals 0, 1 for m sub L equals 1, and 1 for m sub L equals negative 1. And so that single energy level was actually 3, but they were degenerate, and so we couldn't really see them. And so now we know a little bit more about that, the hydrogen atoms, like the orbitals, the constructions of the orbitals of that atom, and that's just more information for us as scientists to use in further experimentation. Now if we want to add spin into this calculation, we get a diagram that looks a little bit more like this. And so whereas this is entirely consistent with our total angular momentum operator from previous chapters, where J equals L plus S. Here S just equals 0, and so J just equals L, and M sub J equals M sub L. Here we have L equals 1, and then that spin quantum number S equals 1/2. And so J can equal L plus S, which is 1 plus 1/2, 3/2. And so we have J equals 3/2, and so M sub J extends from J to negative J by integer values. So M equals 3/2, 1/2, negative 1/2, and negative 3/2. And then J can equal the absolute value, equal integer values down to the absolute value of L minus S, and so L minus S is 1 minus 1/2 equals 1/2, and so J equals 1/2 also. And so M sub J can equal 1/2 and negative 1/2. And so again, where we would have just seen 2 energy levels, now we see 6. And so again, we had degenerate energies, and now that's lifted by this magnetic field. What we also see is that the Zeeman effect is proportionate to both the magnetic number, and magnetic quantum number, excuse me, and the magnitude of the magnetic field in both cases. So why is this interesting to us? Not only does it give us more information about the particle, it gives us more tools to use when looking at other objects. And so if we look at the sun, for instance, if we're using spectroscopy, we might see something that looks like this if we're looking for hydrogen. And so we'd look at that and we'd say, okay, the sun has no magnetic field. But now if we see this instead, we could say that the sun has a magnetic field. But what else could we say? The yes or no answer is rarely satisfying. So consider if instead we had seen this. In this case, you could say that the magnetic field of the sun was stronger than if it was this. And so now we also have a value associated with it. And so this can give us information like whether or not the object is spinning. If we're looking at stellar objects, that's really important. And it can tell us the orientation of the spin, and so we can see kind of where it's pointing. And that's all very interesting information. But now consider if you're a scientist and you're expecting to see something like this, but you see something else instead. Did you wonder why we called this the anomalous Zeeman effect, even though it was really the full Zeeman effect? Well, first scientists knew about the normal Zeeman effect, and it fit their calculations nicely. But then they saw something. When they were expecting to just see the normal Zeeman effect, they saw spectroscopy that looked more like this. And they accounted for all factors They knew that there was only hydrogen and there was only the magnetic field that they anticipated, but they couldn't figure out what this was. And so they knew it was a Zeeman effect, they just didn't know why, and so they called this the anomalous Zeeman effect. Eventually, a man named Peter Zeeman was able to attribute it to the spins of a particle, and he was able to basically unify the Zeeman effect to a single cause, and he won the Nobel Prize in 1902 for it. And this is the basis upon which much of quantum mechanics today is built, which allows us to do things such as create quantum computers, which are kind of the future of computing, and that's all very, very interesting. And so that's very much the heart of the Zeeman effect. Thank you.